So first, your name, please, and your specific field of study.
My name is Ashok Shukla, and I work in materials electrochemistry with emphasis on batteries, fuel cells, and supercapacitors.
Would you mind maybe recapping some recent discoveries or occurrences in your field?
Yeah, actually batteries, if you look at the batteries, there's a lot of developments have come, but as was indicated by Professor Taraskan in the morning, they are far off from the Moore's law. You know, it will be impossible to match the Moore. It's not a law. Of course, Moore's law is not a law, but then you see it has worked very well in building chips and miniaturizing the computers. But in the case of batteries, it will be hard to see.
So today, I remember during your lecture, we spoke about, or you spoke about electric vehicles. How many different types of alternative energy vehicles are being researched or currently being used in the market?
The one is, of course, hybrid electric vehicles. Then you have plug-in hybrid electric vehicles, and then full electric vehicles. The amount of battery power varies as you go from one system to the other.
So currently, the countries of Japan and Korea are pushing the usage of lithium manganese oxide, and the United States and China are using lithium phosphate. Which one do you think is better, and which one do you think will become more mainstream in the future?
Lithium manganese dioxide is if you look at that, is not that attractive. It is, we call it 131313, that is manganese, cobalt and nickel. That is attractive, but it is also not safe.
How the state of charge regions of battery operation, particularly for lead acid per se, you find that most of the cars that you have, for example micro and conventional cars, they are working in the state of charge in this region about from 90% above. In that situation, lead acid battery apparently is very, very safe, and it can be charged in this charge because you don't go into the sulfation region. But the moment you go to mild hybrid electric vehicles, when I say lead, it is a lead oxide activated carbon plates. That means you now get rid of the lead plate completely, and hence you mitigate this problem. So, where the standard lead system has been now replaced with the lead positive and the carbon negative. And of course, Firefly energy, for example, has used the negative active material in three-dimensional phases, and therefore they have tried mitigating the problem, and the problem still persists. You can also, as has been indicated by, you can go ultra battery route, wherein you can have the lead electrode. This is the conventional lead battery. You can go now. Axion has a lead carbon route, and then you combine the two. Therefore, you end up with the lead, partly carbon, and the lead oxide positive. So this way, you can, when it is a fast charge discharge, you can use the lead carbon combination, but and the conventional operation, when you are using for a long range application, you can go for a lead combination. Well, these are the combinations we tried, and they have been pretty successful. I must present here the comparison of the data which I have taken from Sangya National Laboratory website. You find that they are now testing, for example, this is the utility partial state of charge cycle application. You find this is the ultra battery. And let us take, for example, lithium phosphate. You find, while the VRLA and these components are failing, you find that the lithium, ultra battery is actually performing pretty well.